Welcome everyone, and thank you so much for joining us today for the Grasp on Robotics series. As a quick reminder, this and previously recorded talks can be found on our YouTube channel and website. Also, throughout the talk, please submit your questions using the Q&A button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. Now, I would like to introduce our GRASP faculty host for today's talk, Dr. Mark Yim, GRASP Director and Asa Whitney Professor at the Mechanical Engineering and Applied Mathematics Department in the School of Engineering here at the University of Pennsylvania. Thank you so much.
Thanks, Gabby. So as the GRASP Director, it gives me great pleasure to start off this seminar with Ruzena Bajcsy, who is the founder of the GRASP Lab. I want to tell you our structure this time is going to be different than the past. It's mostly just a conversation. The first half will be kind of more talking about the past, reminiscing on things. And then the second half will be talking a little bit more about the future. We have three wonderful panelists. Sid Maya is a postdoc. I believe it's with Vijay's group, Vijay Kumar.
Yes,
and we have Taya Salam, who's a PhD student with Ani Shea. And we've got Max Mintz, who's a professor. I'll give a little bit more. Actually, so I will introduce Ruzena just briefly, and then Max will give a little bit more interesting or personal type introduction of Ruzena. But so just to tell you a little bit more about Max, Max is a professor in computer information sciences at Penn here. He's been here almost 5 decades. A long time, so he overlapped with Ruzena quite a bit. His interest, he's been at the GRASP Lab for a long time in the robotics and sensors areas. And statistical decision theory are the types of things that he has been doing, but currently he's been a little bit more interested in quantum information processing. I know if you are a student who has had a class with him or been advised by him, he's got fans all over the world because he's a fantastic advisor in that case. But let me first, so let me introduce Ruzena, just kind of the more high level things. Ruzena Bajcsy is currently emeritus at Berkeley. She was the director of the NSF SAIS Directorate a while ago. She's a member of the National Academy of Engineering, National Academy of Medicine. She's won all kinds of awards, the Franklin Institute, Benjamin Franklin Medal, the IEEE Robotics and Automation Award, a bunch of ACM awards. She's been doing all kinds of robotics, sensing, and in their interactions with humans. So that's just she started the GRASP Lab 40 years ago. And I'll leave it at that. Max, please take it away from here.
Well, thank you, Ruzena. It is a total pleasure to have a chance to be here today to chat with you and to reminisce. My goal is to get you to reminisce about the beginning of the GRASP Lab. And so let me reminisce about how I first met you and how I first heard about you. I was at the University of Illinois in Urbana at the Coordinated Science Laboratory, and I was about to come to Penn in the fall of, well, actually the summer of 1974. And there was a guy there named Robert Chen who had tried to hire you at UIUC, and he lost out to Penn, but he said, definitely meet Ruzena Bajcsy when you get to Penn. And it was perhaps the best advice I'd ever gotten, because when I met you, it transformed my life. And I would just add that knowing you and Sherman, okay, who were pillars that made life wonderful, both intellectually and in terms of the work we could do, just absolutely amazing. Well, so I recall that you had a single finger robot device from George Girault in a little laboratory that couldn't be much more than 15 feet by 15 feet okay, in the basement of, well, not even the basement, floor 0 of GRW. And you were doing haptics with this device. And I also recall that since GRW didn't really have a basement and didn't have a proper sewer system, there was a faint odor of sewer gas in the air that was, if you will, not exactly great, but you overcame all that and you started the Grasp Lab. So I was hoping you would reminisce about what it took to make that happen, because I don't think folks today can really appreciate what life was like in those days and what it took to make this thing go. And I'm going to stop now and just ask you if you would reminisce about some of this before we get into the more atomic questions that others will ask.
Thank you very much. Can you hear me?
Yes.
Okay. So I remember distinctly, you know, one of the good things about getting older, the long-term memory is fresh. It is the short-term memory that is troubling people like me. In any case, I remember when Max came, 1974, and he came to what they called systems engineering department, and Professor, I think, was it Dorin? No, Dorin, remember?
Yeah.
The chair. Yeah, he brought him to me and introduced me to him and said, well, maybe, you know, we have some common interest. When I came in 1972, January, to Penn. And Penn was well known for the ENIAC, as you know, which was really an electrical engineering feat. And then thanks to all kinds of personalities, really, you know, which is a tragedy, you know, the whole prestige that Penn had in the early 50s sort of slowly decayed. So when I came to Penn in 72, there was a blink of hope that Penn can recover. And the reason for that was that it was a recognition that computer science was becoming on its own, and that it's a subject that can have its own department. So Arvind Joshi, who got his degree actually at Penn in information theory, but also was deeply connected to the linguistics department. As you know, at Penn, linguistics department was quite famous. Chomsky did his PhD there, and his advisor, Harrison, was a quite well-known linguist, mostly anchored in the syntax. You know, that was sort of the basic fundamental principle upon which they were trying to analyze the English language. And Arvind Joshi was designated as the first chair of the computer science. Now, that sort of, and it split from the electrical engineering, which was really the 800-pound gorilla at that time, the Moore School. And that gave Arvind and few others, senior people like Sol Gorn and John Carr III and Rubinov and few others, names that probably would have no meaning to you folks. But in any case, it gave the opportunity to grow and hire new people and set a new direction from the electrical engineering. That was the whole idea, that you wanted to kind of separate yourself from the electrical engineering. And so in January 72, I was hired. I was the first hire for the computer science. It was called Computer and Information Science, and that was on the insistence of Sol Gorn, who really came from mathematics. He got his PhD from Columbia University in mathematics, and he really insisted that basically the essence of computer science is information science. So, so when I came, I was a more experimentalist and theoretician from Stanford, and so I wanted to start a lab. And you know, the good thing about the senior Penn faculty was that they say, okay, here is the space, and you raise your own money, and you do what you want. We are not going to interfere, but we are not going to help you either. So they left me alone, and so little by little, so I had the first master student, Aaron Snyder. I'm still in contact with him, with whom we built the first vision camera system, because at that time there were these solid state one-dimensional detectors, but we wanted to have a 2D detector, so we had to take these one-dimensional slice and move it synchronously around, and that required some electronics. And the other thing we need to do was to be able to digitize the signal. So you see, the digitization went in X direction, but not in Y direction. So we had to build camera system, and we did. And Aaron Snyder was the engineer. As I said, it's such a pleasure because I'm still in touch with him, and he's now retired. Most of my students are retired, but I only retired last. So that was the start of the pattern recognition, and for remaining 6 or 7 years, I really didn't do any robotics, but mostly vision, because that was what I had. John Carr got some money from the National Science Foundation and was able to buy a display. But in those days, folks, there was only these binary displays, you know, cathode tube displays. So they were able to display bits 1 or 2, 1, 0. And that was about it, but it still helped to see. And I taught a machine computer architecture course, which I used with the PDP 11, I think it was, which was able to show how the von Neumann architecture works. And that's what I did. And those were the beginnings. Yes, thank you, Max. So Max came 2 years later. I was an assistant professor. Max came as already associate professor tenure. And I always felt that Max was an encyclopedia of mathematics. Anytime I needed some confirmation or advice, Max knew the stuff. So.
Ruzena, would you like to say something about the people you recruited once the GRASP Lab got started? I mean, Lou Paul and an army of other people?
Yes, of course I would. So I am not sure whether I got my tenure in 1979, and that it gave me a security. And so that also allowed me to think a little bit bigger about what am I going to do, you know, as a tenured professor. But I cannot really remember whether it was before or after my tenure. The first person, if I remember, I hired Sam Goldwasser. Remember Sam, Max? Yeah.
Yes.
Sam Goldwasser was his parents were from Philadelphia, so that helped to recruit him. He came from MIT, and he was a hardware wizard. So with him, you see, in those days, there was very little available in terms of hardware of any kind. So Sam was interested in real-time image processing. I remember he came from that lab, I forgot, from MIT, who were also interested in hardware image processing, so making things fast. So he started to build such a hardware. And of course, I was quite excited and supportive of that. And because I was also interested in real time getting the information from the environment and processing it. Now, in terms of faculty, I have to tell you, so as I said, I was hired 72. I think 73 or 74, Arvind Joshi and I hired Norman Badler. He was the number 2. And the reason for that was that Norm Badler's thesis was in graphics, but it was in motion analysis. And Arvind, we felt that he would fit between us very well because Norm was interested also in the connection of motion analysis with respect to semantic descriptions. And that would be tying to the language problem. So we felt that he would fit between that. If I do vision, the low-level vision pattern recognition vision, and he would do the semantic interpretation, that it would be a very nice triumvirate between me and him and Arvind. What later happened was that Norm had a very good student, Joe Rourke, the Bubble Man. Remember the Bubble Man?
Indeed.
And this was the idea that he wanted to model a human movement. And so the way how Joe was superb in his understanding geometry, and so he constructed limbs and the whole body from the spheres, intersecting spheres. That gave him the possibility of kinematically change in the movement of limbs. And that started Norm's career actually in modeling the human, and from there on moved much more into the graphics area and modeling the Jack and Jackie and all the rest of it. I, in meantime, really wanted to model real movements and real movements, robots. And I got a grant from NSF, which allowed me to buy a Puma robot. And but I very quickly, and then I had a bunch of very good students. Peter Allen, who is still a professor at Columbia University. But before that, I had Barry Soroka, who came from, well, he was my PhD student, and he did some modeling of skeletal modeling of human motion. I had David Rosenthal, who worked on satellite images, the same as Mohammed Tavakoli, who came from Iran. In those days, by the way, we had a very strong relationship to Iran. This was under the Shah governorship, so Penn had a special connection to the Iranian university in Tehran. Who else? I forget. Well, these were, if I remember, these were my PhD students, but they all worked on vision. And so then in 79, as I said, I got the money for buying a Puma robot, and that kind of changed the whole. I was able to do some robotic experiments, and I very quickly realized that the vision is not good enough to interact with the environment, and I needed haptic, the tactile perception, and connected with Georges Giraud from Toulouse. They had a piezoelectric conductive rubber system, and so they made me a little finger, and so that was Peter Allen's PhD thesis. So that's the first 7 years of my career at Penn.
Well, I think, first of all, I would describe you as a force of nature, and that I don't have the proper words to fully explain what all that means, but you are truly a force of nature. I would think that it's time now to let the other people who are on the panel weigh in and do their thing. So I'm going to disappear into the ether here and let them go ahead.
By the way, Max was the one who explained to me much more in detail than I knew the PID control, the feedback system, but Max was who taught me the Kalman filter and the whole Bucci equations and all the rest. And so anyway, yeah, go ahead.
That's really cool. Ruzena, if I could ask you for the benefit of the younger audience to give us a sort of a high-level roadmap of the ideas that you worked on sort of over the decades, just so it would be interesting for us to see how that evolved over the years.
So, as I said, in '79, I got my tenure, and so that gave me a security. So I started to think about what am I going to do next 10 years or so. And I looked around, there were 3 big labs, MIT, Stanford, and Carnegie Mellon. And they had all the big names behind them, you know, John McCarthy, Marvin Minsky, and CMU, it was Newell and Simon. Well, obviously my name didn't match any of that. So I said to myself, well, and I have to tell you guys that they all were supported by the DoD department, DARPA, in a big way, which helped them tremendously because it gave them a cushion. You see, if you were Ruzena Bajcsy or Max Mintz and go to NSF, you know, you get $150,000 or so for 3 years or 2 years. So what that allowed me to hire two students, and that was about it. So the longevity of support wasn't there while these guys had. Now, I have to tell you guys that in I don't know, I think it was in 73 or 4, I think before Max came, the DARPA people have invited Penn to join the DARPA consortium. And I regret to say that some of the senior people like John Carter and Saul Gorn, they said, we don't want any military money. I think they reflected in some ways the after post-war Second War sentiment, you know, that, you know, we don't want to be obliged to the military, which had tremendous consequences, and it took us a long time. Took me at least 10 or 15 years to get back with these guys. So I mean, you know, what I'm trying to tell you that as you go on with your careers, watch the people, you know, their thinking and how they make decisions, because that could have everlasting impact, or at least 10 years impact on the future of that lab. So, any case, I was struggling with these NSF grants, you know, little by little, and but luckily, in those days, so I kind of said to myself, well, I have to be different from these guys. I have to discriminate, and that's another advice I'm giving you. If you really want to make mark, don't be just like a sheep, follow the crowd. It's hard, and you get hit, you fall, but you always have to get up and believe in your idea. That's the advice I can give you. Because if you follow the sheep, like the sheep, then you can make an incremental contribution, but you never will be unique. You will be just one of the many, okay? But if you have some new ideas and you are willing to take the risk and you have a long-term commitment, that's another thing, it's a long-term commitment, then you can make a mark. So this whole idea of active perception came from that motivation. I wanted to be different. I always told my students, you know, when they march that way, I look the other way. And I still do. And I really believe that academia has in some ways an obligation to think out of the box. Okay, if you are industry and you have to make a living and you are responsible for, I don't know, 500 people or so, you cannot take those risks. But in academia, you can. And therefore, you have to be a little bit more adventurous and think out of the box. So this active perception and came from I looked around, I looked what these big boys were doing, and I said, well, there must be another way to do robotics or computer vision or anything else. And so there were two new ideas. One was that came from psychological observation from J.J. Gibson, who said that basically the information upon which we reason and act is not all here, but it's in the environment. And you just take a piece that you need at that moment for the right action. And that was the active perception idea. The other thing that came from just observing people and everything else was that, you know, the human, our biology in general, has more than just vision. Vision and sound, for that matter, is a long distance measurement. But you also need a contact measurement, and that comes from the proprioceptive sensors, which is temperature, pressure, forces, and for some extent also position. So that's how we started I wrote this paper. Why do we need more than one sensor or something like that with Peter Allen? I remember that was in 79 or 80. Yeah. So I hope I answered your question.
Yeah, definitely.
Thank you, Ruzena. So it's clear that you've really been at the forefront of robotics, especially modern robotics.
I did it because I wanted to be different.
Yeah, and this idea of being different has led to very novel and interesting developments. And so outside of the work that you've been doing, from what you've seen, what to you has been the most surprising in terms of developments in the past 50 years of robotics and machine perception?
What has been surprising for me? Well, okay, good question. Well, first of all, as you know, Vijay Kumar joined, well, before Vijay, I hired Richard Paul, Lou Paul. Remember Max? Yeah. And he was a colleague of mine at Stanford. We were students together, although I was older than he was, but we were students together. And as you know, he was the first one who understood transformations of kinematics, rotation, translation. And so he wrote transformation. His thesis basically was a book. And he was at Purdue, and he was not too happy, and his wife in particular was not too happy in where they lived. As you know, Indiana is a quite conservative place, and I think it didn't fit into their lifestyle or ideology or so. So anyway, I was able to recruit him. He came. And I had really great hopes that he's going to, work with us. So, but Lou was alone. Lou, and you can't change people. I have a hypothesis: people don't change after age 5. Those of you who have children probably will agree with me on that. And so Lou was alone there, but he did some nice work. He did some underwater work and raised funding for himself and so forth and so on. But he never did what I was hoping to enhance our visibility and everything else. On the other hand, Vijay Kumar came from Ohio State in the mechanical engineering department I think it was in 84 or so. And he was a junior assistant professor. And so I immediately grabbed him, the gas plant, and he did above all my expectations. He plugged in, and we wrote proposals together and started to build the whole enterprise. And he was extremely influential. Now, answering your question, Taya, was that Vijay started this flying robots, and I never went to that area, partly because that requires much more knowledge about hydrodynamics and the interaction of machines with the air, flying, and all that. It's really knowledge that I just didn't have, and he had that. But Vijay also helped me with hybrid discrete systems. We applied them for collaborating, 2 robots moving together, and he was very instrumental in pushing the kinematics and dynamics. He knew it very well, and he was helping that. So I did the perception, he did the kinematics. The division of labor was perfect, and we were learning from each other. And as you know, it's important to realize personalities. I mean, Vijay is just a nice person, and we trusted each other, and that's another thing. You have to trust in this collaborative environment. You have to trust that you give credit. See, one of the things that I guess by my nature and by my upbringing was that I was not interested to be famous, never. I was interested in that the lab succeeds, that we collectively succeed. And, it sort of brings back, our presidential election when the president says he wants to work for the people. And that's how I felt about it. I wanted to work for the people. And for my students, of course.
Yeah, that's really interesting, especially that you mentioned about how like Vijay was instrumental in beginning the aerial robotics revolution, and how it's sort of really becoming a part of our everyday lives. Like you can see more and more people having drones and playing around with them. We have a question from one of the audience members on sort of another aspect where perhaps robots haven't been as influential as we would have hoped, which is like during the COVID-19 pandemic. So we saw all of these opportunities where robots could have played an instrumental role, but we didn't necessarily see that that like realize. Do you think as a community we are kind of taking advantage of the situation to learn more, or like do you have any ideas on like what we should take away from what we've seen over the last few months, and like how should the robotics community take that and like build on the future?
Well, would you please repeat the question or make it more concise? Because if the question was that what can robotics do during the pandemic, is that what was your question? Or I don't fully understand what was the question.
I guess the summary of the question is, can we learn, what can we learn from the current situation and apply to robotics so that when the next pandemic or kind of these kind of events occur, robots can like really help us?
That's a good question, and I guess I just don't have the answer. So, what can robotics do in next pandemics? Look, it seems to me independent of pandemics, what I think the current technology is doing is helping in services, you know, the delivery of food, the delivery of healthcare of some sort, limited, but healthcare. You know, I think those are the things where the robots can do. I failed to tell you folks that during the 80s, again, as I said, Max was the source of the theoretical underpinning of this whole systems approach that we took. There was a young man from Oxford, I think he came, or Cambridge, Hugh Durand White. And he was a character, very, kind of, very, the room was full of him when he walked in, very, very strong. But he worked with Max, although I'm not sure whether he gave proper credit to Max on that, but because at one point he said, well, I said, you were Max's student. He said, no, I think I was Lou Paul's student. Anyway, there was this symbiosis, and it's typical Max. He has very low ego, so he didn't push on any of this recognition. But the fact is that this whole SLAM idea came from that work of Hugh Durand White. Now, several people came after and improved it, and etc., etc. I hear even today from some of my colleagues like Shankar Shastri, who are critical of that work, but nevertheless, it was the first. And Hugh made a big reputation out of that. In Australia, he had a big institute. I visited him and so forth. Unfortunately, and this is a lesson for you guys again, if you don't know your limits, it will work against you. And you overplayed his hand in Australia. And I don't know if he had to leave, but he certainly left. And now I think he is in England. And his family is divorced and so forth. So you have to be careful. You have to know your limits. That's another moral.
Great lesson, Ruzena. So you talked a little bit about how currently robots are being used for things like delivery services, and it's clear from all of the interests that we have surrounding robotics, they're going to be more and more prevalent in our society.
Right.
Well, an ongoing theme, however, has been pretty much since the inception of robotics has been this fear surrounding robotics, right? And so I'm wondering if you feel as though the perception of robotic has evolved either socially or commercially, culturally, and exactly how realistic is our current vision of robotics?
Well, it depends whom you talk to, but I always felt that robots should help people and that they should work in a symbiotic fashion, but in a helping role. Now that's, not always the case by many people, Elon Musk and people like that, feel we will have autonomous airplanes, autonomous this, autonomous that, and that ignores actually human in this play. I don't share that view. So I think if you take my view that the robots have to somehow live with us and should be helpful, then your approach to the whole ethical question of how will you make robot to be, how will you program actually the robot so that it doesn't harm you, okay, is really a outstanding question at this point, because we don't have fully conquered the fact how to control the robot in such a way that it will not harm. I mean, you have heard all these accidents that happen. Now, I can tell you that even, some people may think that working for the military is not always ethical, etc., etc. I don't share that view, because you have situations where you have elements of the society that need to be somehow contained, and the way how you contain them is through some kind of military action. But I can also tell you that in my career meeting several generals, they are just as concerned about ethical issues, as you or I are. I mean, when these guys sitting at the table and are planning, how to do this or that, they feel the tremendous responsibility of the consequences of their decision making. So the decision making, especially now that AI is big hype, and want to make the machine decisions, these guys are not taking it lightly. So anytime you have a technology that has an impact on the society, and this is not the first time. I mean, during the Industrial Revolution, we had, tremendous shakeup of the society. And so, the other day I was listening to somebody about the ethics of robotics, and they were saying, well, maybe we should stop working on many of the technologies. Well, let me tell you, I don't know you guys, but I would not trade doing the laundry by hands, which I used to do when I was very young, for the washing machine. I mean, then the dryer you have. So certain technological advances are really helping in our lives. So we have to be judicial, and we have to mind what is it for, what we are doing.
That's a really interesting question, and it's a good segue into the next question we have, which is you mentioned this whole idea of like how there were many universities that were dominated by DoD and DARPA-based funding, which raised this sort of issue of ethics. And so the question is, what are the implications of the robotics research being funded by government versus industry? Like, do you have sort of ideas on the trade-offs between the two? Separate from NSF and things like that?
Well, Max knows I was married to a physicist, and physicists always argued, at least the particle physicists, that they always argued that there is no other way to support, the understanding of the universe except by the collective support, which is really the governmental support. Now, some of these environmental, biology, you name it, problems. The problem is that if it's going to be supported simply by a company, okay, or individual, then these individuals have an agenda. And that doesn't, and companies have an agenda. They want to make a profit. So seems to me that if you really want to advance understanding and not just developing a gadget that will make you rich, okay, and this is true for pharmaceuticals as well, or anything so that's why we do need the governmental support for basic research, because it is only the governmental support, which is our collective money basically, that allows you to explore without any guarantees of return on your money. Okay. Now look, I'm a big history buff. If you look how in, let's say, Galileo or Copernicus or these guys, how they were supported by the kings. Later on, the Pascal, the Newton, the Laplace, these guys were rich. So they sort of use their own personal money, okay, to do. But then when we come to end of 19th century, beginning of 20th century, when the science is beyond an individual, as you know, probably from Vijay, poor guy, he goes around and he's constantly asking for money to support the university or the school agenda. Okay, because individual doesn't have enough to just say, okay, for improvement of the human being. And education is part of it. So I, for example, pay for all of my grandchildren education because I believe that that's the future.
Yeah, I think one common theme that you've touched on is technology and science, and how the benefactors of technology and science should really be the people, right? Where we should build robotics to serve people to fulfill some societal goal. So in terms of how things are progressing now, do you feel as though technology is giving more power to those who are already powerful, or do you see this this shortening of the gap that exists between those who are powerful or not as privileged, which seems to be in your opinion, the goal of what technology should be?
Well, look, it's undeniable that the networks have democratized And that's a technology that started to evolve in the 50s, right? And it democratized a lot of the access to information and communication and so forth. Is it all fair? No. I mean, if you go to rural areas, and that's why I said that Mr. Trump is just a reflection of all these differences that we have in our society. Because if you go to rural areas, they barely have connectivity of modem, you know. And so think about, those kids who are just as bright as my grandchildren or you or so, but without access to the information, they will stay behind. They will not be as competitive as you or I are. So again, I approve Joe Biden said that he's going to improve the connectivity in the rural areas. And it is critical. It is really critical. I like to watch some of these travel shows. So there was a very nice show about Switzerland. And it's incredible that 100 years ago, those guys built trains in these very mountainous areas, which gave the population access. They could live there, but they could go to other places and learn. So we all collectively have to somehow see that, technology gets distributed. It's not sitting only in the Amazon hands. Think about what's happening now. Think about these kids who are growing up in these neighborhoods where there's no father, only the mother. She has to go to work. And the kid doesn't have access to the internet. That whole generation will be left behind. I think Mark thinks that maybe not. I hope you're right, but I hope not. But I'm worried because there is a certain very particular age, and I watched this from my own children and grandchildren, is around between 5 to 7 to learn the kids how to learn. To learn how to learn, to have them confined and focused. Do your homework. And if you are not there, they won't do it.
Yeah, one of the things that have helped more and more people get into robotics has been these explosion in standardized hardware and software platforms,
yes,
right?
Yes.
Comes to ROS, PR2, Baxter kind of platforms. And there's no question that it's helping more and more people get involved with the science, which is fantastic. Do you see any pitfalls for academicians to kind of over-rely on these kind of standardized platforms? Do you think it could, there's something we should be aware of in terms of like doing research as we get more and more sort of streamlined into these standardized platforms? Or do you think it's an unequivocally good thing?
Well, as you can imagine, there is no real binary answer to that. It's good and not good. The good part is that in teaching, it helps. That you have that you don't have to go to the bits and bytes as I had to do it 60 years ago, and that the students can just use the ROS as a standard operating system and use modules. I mean, many of these kids don't know how computer vision work. They just apply a module and blah, blah, blah. So that's helps in bringing them up so that they can do whatever else they want to do. The bad thing is that most of the time they don't bother to really learn what's behind it. And, and that is really bad. So here is my take on that. It's not accidental that we have high schools, then we have community colleges, then we have undergraduate schools, and then we have graduate schools. So depends on what your ambition is. You just may want to learn how to do things, and for that, you probably don't feel compelled to really understand what's behind it. But if you are at the place like UPenn or Berkeley for that matter, or any of these schools, you better understand what is behind it.
Yeah, so there are a lot of questions on moving forward, how we can better integrate robotics and robotics curriculum. So everyone from elementary school students to, graduate level students can understand robotics. And one thing that here at Penn, we take an integrated approach to robotics, right? It spans across multiple departments. Other institutions have dedicated robotics programs, for instance, Carnegie Mellon.
Yes.
And so this is also true, University of Michigan is trying to create a dedicated undergraduate robotics program. So what are your thoughts on having these dedicated robotics programs versus a more integrated approach where you combine multiple departments? And what implications does that have in terms of what we're actually teaching about robotics?
Okay, so I will tell you the following. I would not recommend my grandchildren to go to these specialized robotics institutes or courses or I would definitely suggest to them that they should pick up as broad background in mathematics and physics and perhaps biology and chemistry as possible. And here is the reason. Since I care that my grandchildren outlive me and be productive way after I am gone, you really don't know what will be the next 20 years of challenges. But you do know that just like as you are building a house, you need foundation. So you do know that certain foundational knowledge will be there. So for example, you know that Newtonian physics or mechanics will be here as long as we live in the gravitational world, period. Okay, so you better understand that world, and you better understand the dynamics of Lagrange and Hamilton, because you know that things will not be just stationary, that we move, the universe moves. Do you see what I'm saying? So it seems to me that, and the same, for biology. Look, used to be, that you had doctors who would touch you and listen to you and so, but today, the whole healthcare science is based on some observations that are using physical and chemical principles. And chemistry is in some ways depend on what scale you are looking at is physics. So you better get those. And as I said many times, and I repeat, learn it while you are young. It's much harder to do it when you get older. I still do it, but believe me, I had to write and rewrite and go through the examples several times before it kind of hits. So for example, the fact that Max is teaching this quantum information processing baffles my mind because, you know, it's complicated, but it's important, it's coming. And those computers will be here because they compute much faster than your von Neumann machine. On the other hand, they are specialized. They will not do every algorithm that you can put on the von Neumann machine. So the same thing that, you know, when I was young, I was working on analog computers. You probably never heard of them, but anyway, I worked on those. And they were, of course, superseded by the digital because the digital was much more flexible. And the one big drawback of analog computer was that the zero was fluctuating. Zero, never knew where was the zero. However, now, because of all these optimization algorithms for these large feature sets, people are starting to look into some specialized analog computers that would quickly compute the gradient and look for optimum. Yeah, so wherever there is a good reason for specialized computers where you really need to compute fast, you know, like in cryptography, for example, makes sense to make these analog or quantum computers.
Yeah, that's
But
a really
again,
good.
you need to understand what they can and what they cannot do. Yeah, go ahead.
Right. Yeah. So I was going to say it's a good reminder for us to keep thinking out of the box, keep looking
Absolutely, absolutely. Be your own man.
That's right. So as roboticists, we are always thinking about how to build robots that could help people, that could help improve their lives.
Not always,
right? But
not always, but it's most of the time. Good.
Yeah, we would like to think that we are,
yes,
thinking about it.
Yeah, good.
But it's a different problem to be able to convince people that robots would actually be something that they should adopt in their lives. That's kind of a different part of this challenge of getting robots into society. So as roboticists, how do you think we could kind of address this negative perception that a lot of people have on kind of having robots milling about them?
Good question. And actually, I wrote an article somewhere. I don't remember where. I think ACM Moshe Vardi asked me to do that or something like that. Robots and jobs. Okay, so look, for many people, you know, let's take the high school graduates kind of, you know, robots are threatening that the type of jobs they would have had will be taken up with the automation. Okay, and it's a real. You see, jobs is not only getting your paycheck, but it's also feeling that you are useful, that somebody needs you, somebody wants you. So it's a complicated thing to have or not have a job. But so I always felt that that if we create some automation, whether it's in an assembly line, which is taking place now, the question is, there is a profit, right? And how should the profit be distributed? Okay. So I give you, I remember in that article, I used the following thing. I have a cleaning lady who comes into my house and does vacuum and few other things, cleans. And I pay her, I think at that time was $70. So now I pay her $80 for coming. Now let's suppose that I buy, Rodney Brooks's little vacuum robot. Or maybe I get a more sophisticated robot that can other surfaces that my cleaning lady does. All right. So let's say that that robot cost me that robot cost me I don't know, $3,000 or $5,000, whatever. Okay. And I amortize this $5,000 over a certain period of time. But after that, I am making a profit because I'm not spending the $80 2 weeks to my lady. So how should that profit be distributed? And how much my cleaning lady should be getting some of it? So I think that's where the issue of taxation comes in, And that's, again, is a matter of fairness. And it's unfortunate that we as human species have this property called greed, and you really need to educate people not to be greedy, but be, because how much does an individual need? How much Jeff Bezos need all those billions, right? And that's really the issue. That's where the ethics and fairness comes in.
Yeah, so as roboticists, we have a long road ahead of us, many challenges to come, but we would love, our time is coming to an end, so we would love
I see that, yes.
some parting advice that you have from the audience, for the audience would be great.
Well, if you are in the beginning of your studies, take as much math, physics, and maybe biology as possible, as your schedule allows you to do that. That's number one. Number two, be curious and learn from the past. It's not just what the elders did or didn't do, but it's their way of thinking, how they got to a certain decision or result. It might be useful, the thinking process is useful. And then question your consciousness, why I am doing what I am doing, and what is this good for?
Well, thank you so much, Ruzena and Mark, Max, panelists, for joining us here today.
Okay, and now I have to switch, right?
Yeah, now we'll switch over. Just give me 2 seconds, Ruzena.
Yes.
Thank you, everyone that was able to join us here today. Please tune in next Friday, November 13th at 11 a.m. Eastern Standard Time for the next Grasp on Robotics speaker, Dr. Nook from Iowa State. And then if for more information on upcoming events, be sure to follow us on social media or check out our website. Thank you so much and have a wonderful day.